Hello Mindsetters, welcome to today's Grade 12 Geography show on Mapwork questions, proudly brought to you by Macmillan. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
We will be using today the topographical map of Rustenburg. Now, what we will focus on is the following. The question: calculate the magnetic bearing. Immediately, once I see the magnetic bearing, I should remember that I'll have to be calculating the true bearing as well as the magnetic declination of trig beacon J7, trig beacon 228, which is in J7, from trig beacon 46, which is in J5, for the present year. Now, for the present year, we must remember that you take your present year and subtract it from the year on the map. I've already indicated to you that the map that exists is the year that the map was printed, and we have to calculate in order to understand the following. Now let's go to the map of Rustenburg West. Note that the information given is contained on the margin of the map. Here we have the following information. The mean magnetic declination, which is 15 degrees 57 minutes west of true north. This particular map was printed in July 1997. The mean annual change, which is 2 minutes westwards. You should remember the following. When we're recalculating this particular example, we will understand what the difference between the westwards and the eastward annual change is. So I want you to focus on the following. The marginal information, the information that is contained in the margin of the map, refers specifically to magnetic declination. The 2 points in your question, as you will see, refers to specifically the true bearing. Let's go back to the screen. So we have the following. Trig beacon 228 in block J7 and trig beacon 46 in block J5. What I've done for you is prepared for you a screen of this particular section of the map. Let's look at our 2 points. Note the following. There's our trig beacon and there's our trig beacon 46. When you analyze this particular type of question, you have to focus on the from point. Now, what I'm going to do for you is do it on the topographical map. Note that I have to have my ruler. And in order to calculate the true bearing, I must remember the following. My 2 points. My points are as follows. Trig beacon 228 and trig beacon 46. In this example, I've been asked to calculate the position, the relative position, the true bearing of trig beacon 46 from trig beacon 228. When I'm analyzing this particular question, the from point on your question is trig beacon 228. So let's go to our from point, which is 228, and remember, I will draw a straight line at the from point, like so. Now, this is what we call a true north line. The true north line gives me my position in relation to the geographic north. The geographic north is my position at the top of the map. Notice that is what we refer to as true north. Once I've done the first step, I should remember the following. Step 2, join the 2 points. With my ruler, I take from the from point and look at the other point and draw a line joining the 2 points. In this example, we use the following. Trig beacon 228 and trig beacon 46. Note that the from point in my explanation is 228 and the other point is 46. However, let's look at another hint and tip. If I had to change this question, I would make the from point trig beacon 46. If trig beacon 46 was my from point, I'd be drawing a true north line at that from point. Now, in order for you to remember this, you have to remember the word from is crucial to the 2 points. Once you've established which is your from point, according to the question, you will draw a true north line. Now, let's go back to the question and understand it. Calculate the magnetic bearing of trig beacon 228 from trig beacon 46. In this example, it is trig beacon 46, which is my from point. So what do? I go back and remember the angle from the true north line to the other point. This angle here is what we call the true bearing. The true bearing would measure the angle between the true north line and the other point. Now, we've already used our protractor and measured this angle, and we've received it as 80 degrees. What is also important is to remember the following. In true bearing, you have a direction. If this is north, this would be south, like a compass. There's my east, and you'll note that between north and east is northeast. So between northeast and east will be, in order for us to understand the following: the directional arrow of true north, the east line, remember the following: true north line, line joining 2 points. So I want to repeat the steps to you. The first step is to establish the from point. The from point in this example is trig beacon 46. Trig beacon 46, the other point is 228. Trig beacon 228. Because the from point is trig beacon 46, you draw a true north line at the from point. Step 2, draw a line joining the 2 places and then measure the angle. In this case, the angle that was measured is 80 degrees. Let's go back to our question. So, in this map, we'll do the following. I'm going to draw a line for you to show you how we get to the answer. In this example, and we'll note that the true north line is exactly crossing your trig beacon. That's my true north line. Let's draw the line joining the other 2 points. In this example, so the angle between the true north line and the line joining the other point is what we refer to as the true bearing. The true bearing refers to the 2 points in relation to each other. In this example, my from point is trig beacon 46. Let's look at the calculation. 80 degrees east of southeast. Let's change that to east of northeast. As we've established, the line lies between east and north, so it's going to be northeast. Note that in this example, the angle is on facing your eastern half. So you've placed your protractor towards the east, and therefore the angle would be less than 180 degrees. When looking at the calculation, let's look at the information that we've extracted. The mean magnetic declination, which we've seen as 15 degrees, 57 minutes west of true north. This is information that we've gathered from the margin of the map. The mean annual change, 2 minutes westwards. Also information that we've gathered from the margins of the map. Let's look at the next step, number of years. As we've established already, you should note the question requires you to calculate the magnetic declination for the present year. In this example, our present year is 2014. As we've established from the margin of the map, the year is 1997. 2014 minus 1997 is 17 years. This is the number of years between the present year and the year on the map. Once we've established the number of years, note that the year is multiplied by the mean annual change. We've taken this mean annual change, we're taking the number of years to calculate how much the change is of this declination. 17 times 2 is 34 minutes. What I would like you to do is always ensure that you convert your 34 minutes to degrees and minutes. So simply put, you'd write this answer as 0 degrees and 34 minutes. Now we are ready to calculate the magnetic declination. Note, the mean magnetic declination remains 15 degrees and 57 minutes. We add. Why do we add? Our mean annual change is westwards. Whenever the mean annual change is westwards, you've got to add. Whenever the mean annual change is eastwards, you've got to subtract. As we've looked at the marginal information, this particular mean annual change is westwards, and therefore we're taking our mean magnetic declination and adding it to the total change, which we've calculated already as 0 degrees and 34 minutes. Our total for the magnetic declination is 15 degrees and 91 minutes. The problem with 91 minutes is this is greater than a degree. What you should note is the following. 1 degree is equal to 60 minutes. Therefore, in 91 minutes, there is already a degree. So we need to convert that degree further. And what answer do we get? 16 degrees and 31 minutes. What I've simply done there is taken the 91, taken out 1 degree, which is 60 minutes, and added that to my remainder to convert the final answer to 16 degrees and 31 minutes. Now I'm ready to calculate the magnetic bearing. The magnetic bearing, according to my formula, is true bearing plus the magnetic declination. Note, I've calculated the true bearing to 80 degrees, as well as my magnetic declination to 16 degrees and 31 minutes. Once I've got these two answers, I am able to convert that. 80 plus 16 is, oh, we've got a problem here. 80 plus 16 is 96 degrees. And there's no minutes here, but there's 31 minutes there, so that's 31 minutes. I would discard this answer, and remember, it's east of northeast. So, most of our learners write the following answer, west of true north. I want you to remember, you carry your direction from your true bearing down to your final answer. Your direction from your true bearing is carried to the magnetic bearing. Let's look at that again and what we've done. We've calculated, for an example, the magnetic bearing of trig beacon 228 from trig beacon 46. Once I've got my question, I am able to understand the following. There's 2 points on any topographic map. What we have to establish is which of the 2 points is the from point. The from point in this example is trig beacon 46. From trig beacon 46, I draw a true north line at the from point. Step 2, I join the 2 points. Once I've done that, step 3 would be to measure the angle. Once I've measured the angle, I've calculated my true bearing. My true bearing must be attached to a direction. Let's go further. Once we've established the true bearing, we now calculate the magnetic declination. All the information on the magnetic declination is contained on the side of the map. In this example, the magnetic declination is 15 degrees, 57 minutes west of true north, which is found on the map. The mean annual change, also found on the map, is 2 minutes westwards. The number of years, remember in our calculation, we are calculating the present year, subtract the year on the map. The year on the map is the year indicated immediately after the west of true north, which in this case is 2014, subtract 1997, which is 17 years. 17 times 2, we've received the 2 from the mean annual change, which is 34. And that answer, 34, is 34 years per minute. We convert that to degrees and minutes, and therefore we write it as 0 degrees and 34 minutes. Once we've established the total change, we now can calculate the magnetic declination. The mean magnetic declination, which we've established as 15 degrees 57 minutes, plus, remember, this particular sign changes according to the annual change. If the annual changes westwards, we will add. If the annual changes eastwards, we would subtract. And therefore, 0 degrees, 34 minutes, which is our total change. Degrees to degrees, minutes to minutes. In this case, 15 plus 0 is 15. 57 plus 34 is 91. Note, the moment your minutes is greater than 60, you will be required to convert that to degrees and minutes. And 91 minutes can be 1 degree and 31 minutes. Remember, I asked myself, how many times does 60 go into 91 and what is my remainder? 1 time, therefore 16, the remainder 31. Once I've established my true bearing and magnetic declination, I can now calculate the magnetic bearing. Hence my formula, magnetic bearing is equal to true bearing plus magnetic declination. The true bearing was 80 degrees, the magnetic declination 16 degrees 31, which we've calculated. We add the two, 80 plus 16, 96 degrees. There's no minutes here, the 31 is carried over, and we add the direction from the true bearing. So, simply put guys, this is the basic calculation of magnetic bearing.
Okay guys, I hope you're enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
Let's look firstly at the type of question you will receive for this type of example. Refer to the topographical map. Let's get our pens in there. Refer to the topographical map of Graaff-Reinet. The first question that we'll be dealing with is the following. Calculate the position, and note always your position is calculated in terms of its relation to the equator, which is south. We are south of the equator, and the Greenwich meridian. We are east of the Greenwich meridian. Of Trig Beacon in 87 in block A1. And for this example, we're going back to Graaff-Reinet. And let's go up here. And there's block A1. Note the position of Trig Beacon 87 in block A1. This is the full map. We've managed to extract this map. But what I want you to note is we're using the same degrees and minutes. So let's go back to the question and look at the map. We've managed to get an extract of this map. Our step-by-step process will lead us to the answer for degrees and minutes and seconds. Note, the degrees and minutes are read off the topographical map. The seconds are calculated. Let's go straight to the map and understand the section. So firstly, for Trig Beacon 87, I would have to draw a line from that point to the top line of latitude. Note this example, the latitude is 32 degrees and 15 minutes. Let's look at the longitude from the point to the line to the left. And in this example, note your line of longitude is 24 degrees and 30 minutes. Longitude, 24 degrees and 30 minutes. What I have to do is calculate the seconds south and the seconds east. Let's help you with that. So, what have we done? Step 1, determined the longitudinal coordinates. Step 2, determine the longitudinal coordinates. Step 3, measure. Note, when we're measuring, we're always going to measure in millimeters. This is a more accurate determination of the distance between the line and the point, between the latitude and the point. And step 4, measure again, as well as remembering that it is in millimeters, the distance between the two latitudes. I'm going to go further and check the next step. Step 5, measure again in millimeters the distance between the longitude and the point. And step 6, measure the distance between two lines of longitude. When we do this, we are able to calculate position. So simply put, guys, what you should note is that this distance is in millimeters. This distance between latitudes is in millimeters. The distance between two lines of latitude. The distance between two lines of longitude. I estimated the measurement as follows. I'm going to keep it there. For my latitude, I received 12 millimeters. That is the distance between that line and the point. Over the total distance, remember it's standardized. So always the distance between two lines of latitude, between there and there, or there and there, is always 37 millimeters. And what do we do with this? We multiply by 60 over 1. Where did I get the 60 from? Note, between each line of latitude, the distance is always 60 seconds or 1 minute. 60 seconds or 1 minute. This is the distance between two lines of latitude. When we're looking at longitudes, we should note the following. The distance between one line of longitude and the next is always the same as the latitude, which is 60 seconds, which is equivalent to 1 minute. However, the distance varies, and in this case, I want to draw to your attention the following. The distance between longitudes could be between 31 millimeters to 33 millimeters. I would advise you to always ensure that you secure the measurement of this example. Let's go back to our question. And then when we're calculating, we should note that because of this particular calculation, we should focus on the distances accurately between latitudes, between longitudes, and between latitudes and the point, and longitudes and the point. So this example will be as follows. Note, we've got 12 millimeters over 37 millimeters times 60 over 1. In this example, that's 60 times 12, and I'm going to put it as x seconds. And in this example, further, when we worked out the distance between the line of longitude and the point, we had 15 millimeters. So for the longitude, 15 over 31 millimeters times 60 over 1. And this we're going to put as y. Once we've got these two answers, x seconds and y seconds, we should go back to our original answer. And remember, your x seconds goes there and your y seconds goes there. So this is simply the procedure that you would follow in order to calculate the exact position to degrees, minutes, and seconds. I'm going to move on further to the following. Note this next example, trig beacon 91, and I'm going to quickly go through this. Remember, trig beacon 91 is in block D4. So let's go back to block D4. And in block D4, we have trig beacon 91. Note, with trig beacon 91, we will go to the top line and then across. And when we're looking at it across, we will count the number of lines. Note the line to the top. In this example is this particular line. And the line to the left, in this example, you'd go that way. This is how we use the procedure. We work within the block. And therefore, we'll calculate 32 degrees 51, 52, 53. Let's look at it. 32 degrees, 15, 16, 17, 18. So my latitudinal position is 32 degrees and 15, 16, 17, 18. 32 degrees and 18 minutes. For my longitudinal position, I would move to the left and this line, which is 24 degrees, 30, 31, 32, and 33. And use the same procedure to calculate the seconds. Let's move on back. Now, let's look at the key questions for this particular map in terms of climatology. Name 2 examples of visible evidence on the map that indicates this is a low rainfall area. I'm going to go to the map again of Graaf-Reinet. Note we've discussed this particular map. Note there's an absence of green areas on this map. Because of that, you have non-perennial rivers. You also have furrows and canals, as well as storage dams. Storage dams further emphasize the point that water needs to be stored during the dry season or the lack of rainfall. So in this particular map, it is a low rainfall map. The next question. Determine the north-facing slope of Spandau Kop in blocks B2 and C2. As we've discussed previously, you should note that this area here is your north-facing slope, and this particular area is your south-facing slope.
Now it's time for a break, so don't go away. We'll be right back. Welcome back, Mindsetters. Even though we are selecting highlights from previous shows, you can still follow me on Twitter @LearnExtra, or you can post or comment on our Facebook page. Now, let's do some more revision.
To improve your skills, we will refer to the topographical map of Three Sisters. Three Sisters is in the Klein Karoo region, which is a very dry region and is associated with karst landscapes. So what we will be seeing is different types of formations, especially horizontal type formations, which you've been doing in geomorphology, grade 11. The first question we will focus on is to draw an accurate cross-section from the diggings in B6 to the spot height C6. Before we go to the map, I want you to focus on the following. The cross-section will deal with this particular topographical map and the diggings to that area there. Note the distance between the 2 points which we will be constructing. Note the closeness of the contour lines which we must be able to identify. Note the from point in this example is the diggings, which represents, in this case, a mining area. And the other point is at spot height 1456. Without further ado, I'm going to now go to the manual cross-section that we will construct using an actual topographical map of Three Sisters. So, when looking at this particular section, you will see the following. Our diggings, which is located on the topographical map at this point in block B4. Right, here's our diggings. And we have been asked to construct the cross-section from the diggings, which is a mining area, to spot height 1456. If you've been listening, guys, the first step is to draw a line between the 2 points, like so. So I'll place my ruler like so, and between the diggings and the spot height, I will draw a line. Now my cross-section will determine the shape of the land surface. Because this is a topographical map, it gives us the top view or aerial view of the land surface. What we want to determine is between this point and this point, which is spot height 1456, what is the shape of the landscape? In order to do this, I will firstly get a strip of paper. Using my ruler at the bottom section, I will now use a strip of paper to determine. Note, I'm placing the edge of the paper onto the line that I've constructed. The first step is to ensure that you mark off your beginning point and your end point. And in this example, the digging, which I'm writing down, and in this case, my spot height, which is 1456. Remember, a spot height gives you an actual altitude at that point. Now, what do I have to do? I have to determine between these 2 points, all these contour lines. Note, I'm pulling the strip of paper away, and trying to determine how many contour lines are here. What I've also got to determine is, are the heights decreasing between the digging and that point? Are they increasing between 1419 and there? Note, these contour lines look deceptive, but I'm going to show you a way to easily understand and identify the heights. When determining the first particular contour line, it is a brown line, and the first brown line that crosses is this particular brown line. You will note it flows, and I've got to mark it off here. What is the height of this line? To determine the height of this line, I'm going to pull my strip of paper away and look for the next possible height. You will note that as you move along this line, there is no heights given. No heights given. So I will look for the next possible contour line. And what do I see towards the north is 1160. Let me circle that for you. And that particular line is continuous along this map. And if you note, this is a river system. As you move away from the river system, you should remember the river flows at its lowest point. So if this is 1160, my next line, which is this line, the line in question, is going to be 1180. And remember, that is meters. How did I get 1180? We have established that the contour interval on any topographical map in South Africa is 20 meters. So the difference between 1160 and as we increasing towards this point is plus 20 meters, 1180. And from this point, it becomes so much easier. You should note that as we move along the lines, all these lines will be increasing by 20 meters. Note, I'm marking on my strip of paper the points where the contour lines cross my strip of paper. I should remember the following. If I look at this particular height and the height at this point, the land surface is increasing in height. Each line that passes through my strip of paper is actually increasing by a height of 20 meters. So simply put, my next height is going to be 1200. My next height is 1220. And note as we move along, 1240. Note my 20-meter intervals, 1260. And then as we move along, you will note that this particular contour line is increasing until we've reached this particular point. At this point, which we're going to mark off as X, we should note it's a spot height, and therefore its height is 1419. This is important because these are particular heights that we'll have to establish on our cross section. Moving on, now the heights start decreasing. And for each line that crosses this particular page, we will show you as follows. So what I should remember is, as I move up and further down, now my heights start decreasing. And if they're decreasing, you should note that these lines are now decreasing. So we have now 1260, 1240, 1220. Now note, when I come to this particular stage, I'm looking at this particular line, and it is a common line which touches my line, which is constructed between the 2 points, both at this point and at that point. So it's the same line. What I should be able to determine is that this particular line occurs twice, 1, 2, 0, 0, and again at this point 1, 2, 0, 0. Note, as you move away from the diggings towards the point spot height 1419, the heights are increasing. Once we reach this peak, the heights start decreasing to the point where this particular line, if I pull away my strip of paper, occurs twice along that line. And note, as you move away from 1220, now the lines start increasing again. Already you should be able to determine the shape of this particular landscape. And note my intervals. I've now established that there's many lines that exist, and sometimes I want you to focus in this particular area here now, that in 1492, the closeness of these lines at this particular point means that the slope is so steep that it's almost at a 90-degree angle. What happens is you have a situation where the contour lines start getting much closer together than normal. Although these are steep slopes, because the contour lines are closer together than as opposed to this area here, you'll note that this brown here is darker. What it should suggest to you is that this is an almost vertical slope. Now that we've got our particular markings, we can determine that our highest height at this point is the last point, which is 1456. And as you move away, you'll note that it's decreasing, then increasing to a point of 1419, and then decreasing again. What you should remember is that our from point is the digging. We are required to draw the cross section from the digging to spot height 1456. And I'm going to draw a rough cross section and show you how we actually get to the cross section. To do this, remember, the first step is to determine a vertical axis, like so. Our horizontal axis will be drawn like so. Always remember, the horizontal axis has a scale of 1:50,000. Let's look at the vertical axis. We establish our vertical axis in centimeters. For every 1 centimeter, we should note that there's a 20-meter increase. So what I'm going to do is create 1 centimeter intervals on my vertical axis, like so. Each centimeter will represent 20 meters. I'm going to put in a few more points just in case we have the situation of higher points. Note that my vertical scale is 1 centimeter represents 20 meters. Now, let's go back to our strip of paper. What we've established is that our highest point is 1456. Our lowest point in this example is 1180. And you'll note that if we have to look at our topographical map again, the diggings is a lower point. So it has to start off from the digging. So what I'll do is as follows. I will look at my vertical scale and start interpolating the particular values that I've received from my cross section. The lowest point, and my advice to all of you drawing cross sections is always start off at 20 meters below the lowest point. What does this do? This assists us so that the horizontal axis is not touched. So in this case, my lowest point is 1,180 meters. I will start off at 1,160 meters. And as I progress along, I will increase each one by 20 meters. And note my intervals: 1, 2, 2, 0, 1, 2, 4, 0, 1, 2, 6, 0, 1, 2, 8, 0, 1, 3, 0, 0, 1, 3, 2, 0, 1, 3, 0, 1, 3, 6, 0. Remember, my highest point is at 1, 5, 1, 4, 5, 6. So I will need a few more points to accommodate that height. And remember, I'm at 1 centimeter intervals, so I'm going to increase the number of points on my vertical axis, like so. Note, I'm creating 1 centimeter intervals. Further on, 1, 3, 8, 0, 1, 4, 0, 0, 1, 4, 2, 0, 1, 4, 4, 0. And I'm going to stop at that point because we know already that 1, 4, 5, 6 is our highest point. The next step is to take my strip of paper and place it exactly onto the line of my x-axis. Note the digging. The digging would fall exactly on the vertical axis. We've already established that, and if we go back to the contour, the digging falls below the first line of contour. So it has to be at a lower point. I'm going to put my digging between 1160 and 1180. My first point on this contour line, 1180. Note, in line with 1180, I mark off that point. 1200, I will mark off the point there. 1220, and I will mark off the point there. What I'm currently doing is interpolating points of contours onto the map. And note the closeness of these lines. If I want to be more accurate, I will then use my ruler like so. 1260. My next point is 1419, which is closer to 1420 and just below. Note, I've marked off that point. My next point again is 1260. And I'll mark it off there. 1240. 1220. 1200. And note, in this example that we've used, the 1200 line, which we'll go back to, occurred twice. Note it crossed my cross section at that point as well as that point. So it occurs twice. So when I take my ruler onto that, I will now place it at 1220. And note, immediately after that point, the points start increasing again. And note the steepness of these slopes. One, 2, 4, 0. And my last point, and I'm going to draw this at 1, 4, 5, 6, which is out of the cross section. Now, once I've interpolated the points, this is what I have, a rough cross section. From the digging, which is on my x-axis, y-axis, note there's my y-axis, the digging falls below 1180. From this point, I will now draw a freehand cross section. Note, I am not using my ruler. Now, note that I've missed these points and I will lose marks for that because I've deviated from the shape. However, what I'm going to do is quickly erase that section so that I can redraw that particular points for you. Let's mark off the points again. And then continue. And now we've got the shape. Once we've established this, and I want you to note that this exaggeration, which is a section we will do later on, is showing you the shape of the landscape. This is what we call a cross section between diggings and spot height 1, 4, 5, 6. When we've done this accurately, you should determine the shape of the land. Note, there is a steepness of the slope, and if we look back at our contours, the steepness of the slope, because the contour lines are close together. Let's go back from there to there. Note the decrease as you move away. The contour line starts spreading out, and look at how it decreases downwards to the point where you reach 1200, which is there. And note, there is a point of deviation or a gap between these two, and it's the same line that crosses, and then from that point to that point, there is an increase in height, and you'll note the increasing height. Now this, learners, is a accurate cross-section showing you the shape between the diggings as well as spot height 1, 4, 5, 6. When we do this particular aspect, I want you to focus on the following. The following labels will give you the full marks. The scale of the x-axis, which is 1:50,000. The scale on the y-axis, 1 centimeter represents 20 meters. Remember the hint and tip. Always start off at 20 meters below your lowest height on the strip of paper. In this case, we've had 1180, and my lowest height then becomes 1160. My first contour line, which I'll go back to the map, is at this point. Once I've established this particular point, look at the contour line. Once I've established the height of that contour line, and how did I do that? I looked at the closest contour line to this, which was this particular contour line. And if you follow this particular contour line, its height was 1160. So my diggings lie between 1180, which is this line, and 1160, which is that line. Anywhere in between. Note my construction. At that point, I have my diggings, and I will label that part my diggings. Remember, a diggings is another term on a topographical map for any mining activity. In this case, my final point is here, spot height 1, 4, 5, 6. And this, ladies and gentlemen, boys and girls, is what we call a cross-section. Right? Let's now move back to the screen in order to further identify what it is that we are required to do. So guys, we've been able to draw a cross-section, and I'm going to quickly draw for you a rough sketch. We've managed to answer this particular aspect. Now what I'm going to do for you is draw the actual cross-section. Remember, our diagram is as follows. And the y-x-axis, okay? And our shape of our cross-section, we're going to draw with that particular one, was as such. This is roughly the shape of the cross-section. Let's go back to the questions. Indicate the position of the N1 on your cross-section. Let's go to the map, and I'm going to look at the N1. Note the N1, which runs across my line. It falls between the diggings and the contour line. So, going back to the cross-section, and I'm going to interpolate the N1, which is at this point. N1. The next question. Indicate the position of the non-perennial river on your cross section. Let's go back to the topographic map. And when we look at the topographic map, you'll note the following. The non-perennial river is in that area there and lies between the two peaks. So back to my cross section, and my non-perennial river lies in that area there. Non-perennial river. Let's go further down to the next question. Identify this landform. Note, two areas of high peaks with a river or non-perennial river that flows in between. This particular landform we refer to as a gap if there is no river. In this case, there is a river flowing, so we call this a poort. And with that, we are able to understand the cross-section. So guys, this is essentially the elements of drawing and interpolating a cross-section. Firstly, to construct, you'll need a strip of paper, and then secondly, you should be able to identify the points on a map.
We've come to the end of today's show. Thanks to Macmillan for making the show possible, and thanks to you for joining me and for chatting to me during the show. Please visit our website, learn.mindset.co.za, to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through this year, so stay connected. Goodbye.